Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello, welcome again into this TV lesson running program. My name is teacher Jean-Marie, and I'm here for physics. So today lesson is about physics for the senior 6, and this is a continuation on unit number 5, atomic nuclei and radioactive decay. As you remember, the last time we were discussing on the atomic nuclei and the nucleids. So I hope you all remember. So did you take your time to do more other questions, exercises? That's good. Now let's start by an activity. So this is the activity that I have for you here. The activity is to calculate the energy change in electrovolts equivalent to a mass change of 1 U. I hope you remember this 1 U. This 1 U means the atomic mass unity. I hope you remember from this when we discussed the dimensions and units that we use in nuclear physics, okay? So this is where we have said the unit of mass. That's good. Now we have used the fact that 1 U equals to 1.6 times 10 power to negative 27 kilogram. So here is the answer. What we have to do here is now to say, okay, energy is going now to be in joule, that is one, and this is equal to mass times C. We will get to understand this mass times C after. And we substitute the data. We have the corresponding of this mass, and the C here is the speed of light in a vacuum, and then we have this expression. And then here the energy is going to be 1.494 times 10 power to negative 10 joule. Since 1 electrovolt, I hope you remember again when we were defining this 1 electrovolt, still into the first lesson. We say that 1 electrovolt is the energy required so that the charge moves in a difference potential of 1 volt. So that is a charge, electron charge now. So, and then we have this energy over the one that corresponds to 1 electrovolt, and the answer is going to be this 9.3 times 10 power 80 electrovolts. Well, when you change this, you find 930 mega electrovolts, and this means that because the energy that we have said here above is mass times C square, then C square can now be equal to E over mass. This is equal to 930 mega electrovolts per U. This per atomic mass unit. Now, this C square, we will need it. That's why I have started with this activity, number 1. But make it as an activity, as an example, that we were now determining this C square. I hope you remember what we have also calculated into the first lesson. Now, let's go on today with the 0.52. Because 5.1 was atomic nuclei and the nuclei, but today we have binding energy and mass defect. So you check the physics book. That is the student book for the senior 6. It is the paper page. You have 131 up to 134. This is the reference where you can find some more explanations about this point of today. So let's start with the questions. We have a question 1 there. Mass defect is the point 1 that we are going to discuss. Mass defect. the question here is explain what you understand by the mass defect. Students, to explain this, here's the thing that I want you to know. Experimentally, or the experiments have shown that the mass of the nucleus and the mass of the individual particles into the nucleus is not the same. Do you understand that? This is not the same. The equivalence that is between the two masses is what we call mass defect. Or you can say that is a mass loss. Do you understand? That's good. So it means that when we are going to define and even to calculate this mass defect, we have to think about the composition of this nucleus and then the mass of that nucleus that is given on the periodic tables. Do you know that? Okay. So here we say that the mass defect is what we note, like this. And what I'm saying is that this mass defect is the loss. Is the loss of mass, or that is the mass loss, but into the nucleus. This mass defect is equal to the difference between the mass of the reactant. Okay? So, and then we have again to subtract with the mass of the product. Now, it means that reactant mass, we have now to find it, and then after, we have this mass defect by subtracting what we have. So how can we find this mass reactant? I have defined it. I hope you remember what I have said. Mass defect is obtained from the difference between mass of the reactant and the mass of the product. You have to note that down. That's good. Then here, we have an example, the quick example here. What is the mass defect of rhenium-7? When its nucleus has a mass of 7.01436 U, use the fact that this MP is the mass of proton, and mass of neutron is equal to 1.00867 U. Here we need the reaction. It means that the reaction of the for the nucleus is given by, so students, I hope what we have there for that rhenium, we have the proton, that is number one. We have a neutron, and this gives the rhenium that we are saying that is rhenium-3. You check the periodic table, and this time you are going to find that here rhenium is having the atomic number is 3. And do you remember what we said by this atomic number? That's good. We said it as a mass, as the number of protons. So here we have 3 protons, and then you have 4 neutrons, of course, to give that one. So as what we have said, this is for the reactant, and this is the product. Now let's calculate that. So it means that here we have 3 times, the proton is what is given there, times 1.00728 that is going out to be U. Then plus C 3 times, that is 4 times Z 1.00867 U. So I hope that we have that. So then, remember, you have now to find the product of this C3 times the mass of proton, and then 4 times the mass of neutron. And then see what we now have to obtain. What we obtain is can you calculate that? And then you tell me what you have obtained. We have this, the multiplication, then the sum of the two. And this is what here is what we obtain. We obtain 0.5, then we have 6.5, then 2U. This is the mass of this reactant. And then we have the mass of this product. It was given to be 7.04. 0.14, and that is C3, 6U. Do you remember? The mass defect is obtained from the difference between the two. Is the mass of the reactant, that is 7.05652, U minus 7.0146 U. And then this change gives what? Again, the calculation here, we find 0.04216 U. This is the mass defect. Again, remember what I've said as a mass defect. As a mass loss, that is due to the fact that in experiment, we find this mass of nucleus is not equal, is not the same as the sum of the individual mass of the particles, mass of proton, neutrons we have into the nucleus. And this loss of mass is what we call mass defect. Okay. Now, the point number 2 is about binding energy. Binding energy. Now, students, before we define this binding energy, but I think you are guessing of what it is. Before we define it, let's come back on what we call the Einstein mass energy relation. The Einstein mass energy relation. As it is given here, of course, it is a relation that is between the mass and the energy. It is even a first question that I put here. Give and explain the Einstein mass energy relation with an example supporting your explanations. Now, students, from the special relativity that you know from senior 5, we have defined this energy. But again, let's recall on this energy. So the prediction shows that for any change, of energy, remember this change of energy is for a given of an object, of a substance. There is of a substance. This relates to the change of mass. But this change of mass, it read to the mass change. This mass change is very small, at a very small scale. Do you understand? At a very, very small scale, this is where we say there is a change of that mass. Do you understand, students? Good. Now, let's have an example that is supporting what we are saying here. The example is there. We are saying that is the question number 2 for this one. Let's say we want now to answer that question. But first, when a 1 kilogram mass of water absorbs 4.2 times 10 to the power 3 joule to produce a temperature rise of 1 Kelvin, calculate the increase in the mass of water, the change of that mass. Students, what I'm telling you is that this substance is absorbing an energy, then there is a change of mass. Can you imagine this? But you don't have to expect a big change of this mass, but a small change. You are going now to see through this. So the energy relation here is given by, this is the energy relation. For any change of mass, there is always a change of energy that is given by this relation. The relation that we have defined, that we have given into the activity. And here we have the change of mass times the c squared. This is the speed of light in vacuum. You know this value. So this is what relates to mass energy through what we call the Einstein relation. Then we have the answer. The answer of that, what do we have? We have energy, right? We have energy. This is 4.2 times 10 to the power 3 joule. Do you remember this value? It is even a value that we call the specific heat capacity of water. This is specific heat capacity of water. You know, it is always expressed in joule, kilogram, degree, Celsius, or that Kelvin. So here we have this E, and then we have what else from the question there? We have the mass. What is the c square is what we are going now to find from times 10 to the power 8. This is meter over second squared. And what do we find if we are going to determine the mass? Here we have E over c square, and this is a substitution for 0.2 times 10 to the power 3 joule over 3 times 10 to the power 8. This is the meter over second squared. And then this is going out to give the mass. The mass will be equal to the mass. Can you substitute and then calculate? The mass will be equal to, this is 4.67 times 10 to the power to negative 14 kilogram. Do you see this value? A very small value, very small one. So what we have obtained there, here is the mass we obtained, that is 4.67 times 10 to the power to negative 14 kilogram. This is what is here. This is the mass. Can you expect to find this change of mass when there is a change of energy? When there is an absorption of energy to this material? Exactly no. You can't now detect. As what you see, this change of energy produces just a no detectable mass change. Do you understand? Students, remember, we are discussing on this binding energy and mass defect. But this time it was about the instant energy mass relation. That's good. Then let's have the binding energy. What is the definition of this binding energy? Binding energy is defined because there is always a tendency of breaking up the forces that join the particles of the nucleus together. Do you know that? So it means that, so these are the, it is about the binding energy is the energy that is needed to tear or to break up the individual protons, neutrons apart. It means that it is the energy that is needed now to just to break the intermolecular forces that join the particles of this nucleus together. This is about the binding energy. And the binding energy, the energy needed, this is what I have said, needed to tear the protons, the protons, neutrons apart. If there is any kind of this energy, then we have the binding energy. Now let's again first recall on what is the meaning of this energy. This energy is remember, this binding is a way that you have things stick together. They are held together, the things, the object. You know, to bind a book. Then binding energy, the energy that these particles have in order now to stick together into the nucleus. When you say binding energy, and then in another way, we see it as that energy required so that you break these particles far apart. This was about the binding energy. How can we find this binding energy now, students? We find the binding energy that we are saying here. We calculate the binding energy by applying the instant mass relation. This is the dE, which is equal to d change of mass times c squared. Now guess what? What we have here is the mass defect. Then let's calculate the bar. This is an example. The binding energy for lithium-7. Do you remember what we have determined? Good. It means that this binding energy is going now to be equal to, remember, we have the mass defect times C. The mass defect that we have obtained was obtained to be equal to, we obtained the mass defect equals to 0.042. I hope you are going now to remind me that. So let's have a C squared. Do you remember what you have said? C squared there equals to 930 mega electrovolts per U. Then we can calculate this binding energy, what do we find? We find this binding energy equals to 39. This is 39.2 mega electrovolts. This is the binding energy that we obtain here. Then let's finish this about binding energy on what we have on what we call the binding energy per nucleon. The binding energy per nucleon, this is nucleon, this is A, is defined as this is the binding energy per nucleon. This is defined as the binding energy over the number of nucleons that we have. And then as what you see. Then we can now say that example, find the binding energy per nucleon for lithium-7. And then this is going out to be the answer. You see, we have this REB equals to, that is 39.2 mega electrovolts over 7, because that is a nucleon number. Then this is equal to, this will give, all that you have finished now to calculate, it will give, this is equals to 39.2 over 7. This is equal to 5.6 mega electrovolts. So this takes us now to discuss on what we call binding energy per nucleon of known elements. This curve here shows what we call binding energy per nucleon of known elements. As what you see here, we have the nucleon number, and this is the average binding energy per nucleon number. And this is expressed, of course, in mega electrovolts. So as what you see here, lithium that we came now to calculate is there, as you see, but this is lithium-3. And if you find lithium-7, this is lithium-3, and then you find that is going out to be what? 5.6 around there. So, students, from this graph, what we see here shows that there is an increase of stability of the atoms of the nucleus as there is an increase of nucleon numbers. Do you understand? And then when we reach there at this maximum or at this value or at this ion, then there is a decrease of nucleon, the decrease of binding energy per nucleon. Do you understand? In order now to check on that, I want you to work on this. Find the binding energy per nucleon of helium nucleus. That is a helium nucleus. Then you have now to calculate. Do you understand? And then ensure that this is going out to be around 7. Then I will meet you again by the next time into another next lesson about this unit. Thank you very much for having me today, and I will see you. Bye-bye.